Hello, and welcome to this presentation on how to use the Wolfram Language and Mathematica on your Raspberry Pi. It has been almost 2 months since the initial pilot version was released on November 21st of last year. We've had a lot of positive feedback on this release, especially from educators, and this talk is aimed to get you up and running quickly and teach you how to do some interesting experiments with Mathematica on your Pi. First, let's quickly review how to get Mathematica on your Raspberry Pi. If you have not yet installed Linux on an SD card for your Raspberry Pi, then you can go to the Raspberry Pi downloads page and download the latest version of their Noobs installer tool. As of January 9th, Mathematica is included in the recommended Raspbian Linux option of this Noobs installer tool. Simply follow the instructions from the Raspberry Pi website and you're done. If you already have Linux running on your Raspberry Pi, then you can install Mathematica and the Wolfram language by typing the command shown on the screen at the terminal prompt and following the instructions shown on your terminal. To start the Wolfram language, open a terminal window on your Raspberry Pi or use a tool like PuTTY to log into your Pi from a Windows machine. On a Mac, you can also use your terminal app to log into your Pi using the secure shell command SSH. At the terminal prompt, type Wolfram, which will launch the simple text interface to the Wolfram language. After a few seconds, you will see an in prompt appear. This is the place where you can enter any Wolfram language command, for example 2+2. Once you've typed a complete command, you can hit the Enter key to send the command to the Wolfram engine for evaluation. In simple cases, the answer will appear almost instantaneously. In more complicated evaluations, the answer may take a few seconds. If an evaluation takes too long, you can press Ctrl+C to interrupt the Wolfram engine. This will bring up an interrupt menu where you can type abort to abort the evaluation or exit to exit the Wolfram engine. Here are a few more examples of some basic functions in the Wolfram language. Solving equations, solving integrals, computing the average of a list of numbers, factoring integers, manipulating strings, and manipulating expressions. All in all, there are over 4,000 Wolfram language functions, and they are all documented online at the location shown on your screen. If you want to run the same set of commands repeatedly, you can also place them in a text file and execute them by launching the Wolfram language in script mode. In this example, I create a new file called example.m and enter one print command in it. I then save the file and run it by giving the Wolfram command the -script option with the file name. Now let's take a look at Mathematica, the desktop user interface to the Wolfram language. For purposes of this recording, the Raspberry Pi desktop is running as a remote desktop in a VNC viewing session. You can launch Mathematica by typing Mathematica at a terminal prompt or by double-clicking the Mathematica icon on your desktop. The startup sequence for Mathematica takes about 25 seconds when you run your Raspberry Pi at its regular non-overclocked CPU speed. For the purpose of this recording, I have already launched Mathematica. The Mathematica user interface adds many useful features that the Wolfram language terminal interface does not provide. Most notably, all the visualization and dynamic functionality works within Mathematica, whereas it does not do anything useful in the terminal interface. Let's take a look at a few visualization features. First, a simple two-dimensional plot. Next, let's try to do a three-dimensional surface plot. Mathematica also comes with a dynamic interface, which allows you to build interfaces which update as you interact with controls such as sliders, buttons and input fields, or as variables are updated as part of a scheduled background task. Here are some simple examples. First, let's evaluate dynamic of x, which initially will just display x, but will change whenever x changes its value. So now let's change what x is. For example, we can set x to be 42. And notice that the dynamic output is now also 42. Or we can set x to be a graphics expression. And note how the dynamic expression updates at the same time. Now let's go one step further and create a button which sets x when you click the button. So now let's look at a few examples of how to use Mathematica to interact with hardware on the Raspberry Pi. The simplest case is probably the Raspberry Pi camera board. It can be purchased at online hardware vendors such as adafruit.com. I mention this particular hardware vendor because it also offers great online support to get your hardware connected to your Raspberry Pi. The Raspberry Pi camera board costs about $30 and is a fun piece of hardware that is well supported by Raspberry Pi and Mathematica. To take a picture with the camera, you can use the device read function in Mathematica, which is a wrapper around the RaspiStill command line utility. Here's an example. If you want to take a larger image, you can specify the image dimensions as a second argument, like so. You can also take pictures every few seconds by running a scheduled task. Next, let's take a look at a GPS device. In this case, I'm using a GPS module from Adafruit, which can be used on both Raspberry Pi and Arduino boards. This GPS module costs about $40 and comes with setup instructions on the Adafruit website. This particular GPS module works as a serial device. The moment it powers up, it will begin tracking GPS satellites and start to generate textual GPS data on the serial link. On the Raspberry Pi, there are two ways to make a serial connection to the GPS module. The simplest way is to use a USB to serial adapter cable, which does need to be purchased separately. The second way is to connect the GPS device directly to the GPIO pins of the Raspberry Pi. In this case, you will need to modify the Linux boot options, which is clearly described on the Adafruit website. If your GPS device is connected and working, start Mathematica and open the device on your serial port. In my case, I'm using a direct connection to the GPIO pins, which means I need to use the dev TTY AMA 0 using a baud rate of 9600. The next step is to read the serial buffer. This will return a list of bytes which can be converted to plain text using from character code. The next few steps all revolve around cleaning the data to extract the GPS latitude and longitude. This step imports the full string as lines of GPS codes. This step extracts just the lines that have GPS coordinates in them. This evaluation imports just the GPS coordinates with their latitude and longitudes, north and west. After we've extracted the key GPS data pieces, we need one more small algorithm to convert the GPS device data format to regular decimal latitude and longitude coordinates. For this I've written two helper functions, a convert function and a coordinate function. The convert function converts the GPS format to a regular decimal format, and the coordinates function converts both latitude and longitude and adds a minus sign as appropriate for north and south and east and west. And this gives you the final result, which is the location of the GPS device. Finally, we close to the serial connection. So these are a few examples of what you can do with the Wolfram Language and Mathematica on your Raspberry Pi. But there are many more interesting examples on the Wolfram Community, which is a large user forum with questions and their answers, comments, ideas and suggestions for the Wolfram language. Specifically, there is a group on the Wolfram Community dedicated to Raspberry Pi specific questions, including installation questions, programming questions, and up-to-date product information. I would like to take a few minutes to show you some interesting posts made recently by some of our users. In particular, there are two people who have made spectacular posts on the community, namely Bob Lesueur and Diego Svijovic. Since this talk is pre-recorded, I don't know if they're currently watching this screencast, but I want to thank them for making such interesting posts. This is the main page for the community forum for the Wolfram Language and Mathematica. To help create structure, this forum splits out into different groups for different top-level interests. Let's take a look at the Raspberry Pi group. Here we see individual posts with people asking questions, reporting issues, and sharing some of their ideas and experiments. The first post I would like to share, by Diego Svijovic, is about measuring the acceleration of a ball rolling down an inclined plane. Diego uses Lego for the physical setup of the inclined plane and an Arduino Uno connected to 3 light sensors to detect elapsed time since the ball was released. The Arduino talks to the Wolfram language running on a Raspberry Pi over a serial connection. The Wolfram language code also creates a button which initiates the start of the experiment by releasing the ball. When the data is collected, Mathematica creates a graph with 3 data points, which can then be used as a starting point to test any hypotheses about the physics underlying this experiment. And here it is in action. Another really cool example is from Bob Lesueur, who posted how to build a rudimentary spectrophotometer. All the details are on his blog page, linked from the community page. This setup shows how to build an instrument used heavily in chemistry, biology, and astronomy to determine what substances are present in a sample material. Without going into enormous amounts of details, Bob also uses Lego to create his experimental setup, which includes a bright white light source, a magnifying glass to focus the light on a piece of an old compact disc, which acts as a diffraction grating. This is mounted on a stepper motor, which slowly turns while the light sensor detects the light that is filtered through a liquid and transparent example. This data is then recorded and visualized in Mathematica by using a list plot on the data. The Raspberry Pi website itself also has resources to help you get the most out of using Mathematica on the Raspberry Pi. This website also has a forum with a group dedicated to Mathematica questions. Both the Wolfram Community and the Raspberry Pi Mathematica forum are regularly visited by Wolfram employees to help with questions and post product updates when they are available. The Raspberry Pi website also has a blog where we aim to have regular guest posts which bring product updates and summarize the activities around this product. I need to point out that one place not to look for support is the regular Wolfram Premier service support, since this service is dedicated to our commercial offerings of desktop Mathematica and is not intended for the free Raspberry Pi version of Mathematica. While I have limited experience in the field of STEM education, having taught only college algebra for a few years, I would like to make some connections between STEM and Raspberry Pi and Mathematica. I think that many of you who work hard every day to educate the next generation are looking for ways to make STEM education as interesting as it should be. I was lucky enough to have some really excellent math and physics teachers in high school. Teachers who went out of their way to make science come to life. But that was a good 20 years ago, and I can only imagine with today's resources how much more compelling you can tell the story of science, and how we can use it as a tool to improve our lives. So how can Mathematica and a computer like Raspberry Pi help this field? For science, any science, these tools can be used to collect real-world data, create hypotheses about observations, and test them by analyzing the data. For technology, the Raspberry Pi is a great raw computing device which uses Linux as its operating system, which is an enduring environment used by many scientists around the world. For engineering, the Raspberry Pi is a great simple tool to build simple prototypes of real-world devices, and Mathematica is a nice complementary tool to control and observe those devices. For math, it's obvious that Mathematica is the world's best tool to study and learn about mathematics. It allows you to build algorithms and study them, and then, after mastering the concepts, allow you to build new algorithms and further your understanding. So I hope you find these tools useful, and I hope you can adapt them and use them when educating your class. I would like to end here and use the remaining time in this presentation for any questions, suggestions, and comments you might have. Please type them in the question area of this virtual conference, and if everything goes well, I will answer them live on my phone.